In this video, we'll be talking about the cylindrical coordinate system, and this is the second video after the Cartesian coordinates. So cylindrical coordinates are very interesting, and they too can define any point in space. So it's a good idea to start our exploration by starting at polar coordinates. So most people study polar coordinates. So just a quick review, if you have a grid, and this is still your y-axis, this is your x-axis, then a polar coordinate is given by, we're going to call it rho and phi. So rho is the distance from the origin. So let's do an example polar coordinate. Let's say 3, comma, pi over 2. So that means from the origin I have to go a distance 3, but there's infinite points that go distance 3. So let's say this is 3, negative 3, 3, negative 3. So anything on this circle could be a valid point given just that one condition. But now pi over 2. So using the trigonometric standard, we're going to start here and go up pi over 2, and that means I'm going to go across this line until I hit 3. So this right here is that point that's defined. So that's how we do polar coordinates, as most people know. Now cylindrical coordinates just adds one extra element. It adds the x, y, and z axis. So let's say we have our x, y, z axis. So x, y, z. Now cylindrical coordinates are rho, phi, z. So simply, let's use the same example. Let's use 3 pi over 2. Actually, let's do pi over 4. Pi over 4, and let's do 2. So how that's going to be is it's going to be 3 pi over 4, 2. So we're going to start again at the positive x-axis. It's a little bit shifted now, so we have to keep in mind what we're going to do. So we're going to go 3. So this is going to be 3, this is going to be 3. And so we're going to go on this semicircle. It's really a full circle. It goes all the way back, but we're only interested here. So and then we're going to go pi over 4, and that is 45 degrees. So that's going to be right here. So far I'm at this point, and now I have to go up. That's the last one. So that's 2. So let's say 1, 2. So I'm going to go up here, and it looks like it's going to be right here. So this is my point defined. Let me draw a different color so it's obvious. This point defines my point in cylindrical coordinates. So now we're going to talk about some conversions between Cartesian coordinates and cylindrical coordinates so we can easily transfer between them. And most people learn these as well. So we know that, let's say we have polar coordinates again. Let's say we have this point in polar coordinates. Then this is given by p and phi, right? So we know that this distance is p, or rho, I said p, and this is phi. So this is just basic trigonometry. That means this distance right here is going to be given by rho sine phi, and this distance right here is given by rho cosine phi. So rho sine phi equals y, and rho cosine phi equals x, and that's the x and y conversion. And now if we want to convert the other way, then we see again if we draw our graph, if we have x and y, then using Pythagorean theorem, since this is a right angle, we know that this is radical x squared plus y squared, and that equals rho. And we can find the angle as well, because if we just do tangent of the angle that's right here, let's call it phi. Tangent of phi equals y over x, so phi is given by inverse tangent y over x. So that's the basic easy conversions using basic trigonometry. So now we're going to define unit vectors in cylindrical coordinates. So let's go back to our polar grid for a sec and choose a point. So this is our point, and the point has to come from a circle. So here's the circle. And the point, so this is going to be our unit circle. So it's x squared plus y squared equals 1. And now our first unit vector is going to be called rho hat. And rho hat unit vector is given by cosine phi I hat plus sine phi j hat. Okay, so that's what that's given by. And this makes sense because if we have a unit circle, then this distance right here is simply cosine phi, if this is phi, and this distance right here is just sine phi. So if we add them together, we get this point. So, and then our next unit vector we're going to define is going to be phi hat, and phi hat, you can see that rho hat is going to be perpendicular to the circle because it just follows this direction, but phi hat is going to be tangent to the circle. And in what direction is going to be given by the equation for phi hat. So phi hat equals negative sine of phi I hat plus cosine phi j hat. So that means that if that's here, then this is going to become the negative of the vertical distance. So, and that's going to become the x coordinate, so that's going to go here, and then the positive of the horizontal distance, so that's going to go up like this, and it's going to look like this. And if we impose it here, that's going to be perfectly tangent to the circle. And if we work out that math, it makes sense because it's just the reciprocal formula. So that's tangent to the circle, and it's the magnitude of it is just given by 1, because if we just square this and square this, we're going to get 1. So that's the definitions of those two. And then again, in cylindrical coordinates, we also have z hat, which is just k hat. So the next thing to do is define infinitesimals in our cylindrical coordinate system. So let's draw our xyz grid. So we have x, y, we have z. So let's pick a point here. Now this point had to come from a circle, so here's part of the circle. Then it had to have an angle, so here's the angle, and then here's the z coordinate. So the angle is measured here. This is phi, this is rho, and this is z. Now we have to first find the instantaneous displacement. So pick a point here, and then pick a point that's just neighboring nearby. So let's say this is one on the circle. So the distance from this point to this point, you can see it looks big here, but it's supposed to be instantaneous. I drew it big so we could understand. So to get from this point to this point, we have to take a few steps. So first thing we have to do is we have to define where is this point located. So it's going to be, if this length right here is dp, it's dp, which means very small displacement, then the unit vector, the vector has to deal with this, is going to be dp times p hat, right? Because p hat would just be a unit vector, so dp will times dp is a scalar, so that's going to give us the full vector. So from there, we're going to curl around this way until we match the angle of that point, and that's going to be given by p times d phi times phi hat. And to understand that really fast, use the formula S equals r theta, the arc length formula. And the theta in this case is d phi, because we're going from here to here, so the change in phi. And then the radius is just rho, and then we have to use the unit vector to make it a vector. So, and because even though this is curved, we're going to say it's just the displacement vector, because it's so small we can consider it straight. And then the last thing to do is just standard plus dz times z hat, and that's just standard because that's just from Cartesian coordinates. So this formula, and it's going to be, let me write it in a better, so the formula ds equals dp times p hat plus p d phi times phi hat plus dz times z hat. That's going to give you the displacement from one point to a point that's instantaneously close to it. So now let's do the last few things. We're going to define surface area. So if we have, again, this, and if we actually draw a cylinder upon here, then coming from here, let's say we have a very small little patch of surface area that's just on the surface of the cylinder. Then that patch is given by dA, the instantaneous area, infinitesimal area component is given by rho times d phi times dz. And we can see this like this. So if this is the patch, then rho times d phi gives you the change in the arc, because again S equals r theta, and then r is rho, and then theta is d phi. That's going to give you the length, and since even though it's curved, since it's so small, we can treat it as straight. And then dz just gives you the height. So it's as if it's a rectangle, even though in reality it's a slightly curved rectangle. But because it's so small, we can ignore the curvature. So dA equals p times d phi dz. Now the last thing to talk about is the volume. And so we have a volume element. It's going to be coming out here, and it's basically the surface area given some depth. So we're going to give it some depth. And that's going to be simple as dv equals p times d phi. And remember, that's the arc length, which we can treat as straight, times dz. So again, that's just the height. And then we're going to just add a dp here. D rho, okay, so D rho. If I say P rho, I'm sorry. So D rho, and that's just because it's going to be the change in, that's the depth from the outer surface to the inner surface. So that's our instantaneous volume. And that's really all there is about cylindrical coordinates. In the next video, we'll talk about spherical coordinates, which gets some more complicated, but they're pretty useful.